Welcome, students, to Wednesday, and it is March 25th, Organic Chemistry. All right, so we have been working through the PG 23a. We did the first models 1 and 2. Today we're going to do model 3, and then we're going to go to PG 23b. Some announcements that I will be making is we are going to move, we're going to give us more time on the enols and the enolates. So I will be moving your Quizam 4. We're going to change that date. Also, it's an announcement. Your Quizam 4, which will likely be on sapling. Okay, it will be half a part on sapling, multiple choice, and then your open response will be probably just a PDF format like we did on the Quizam 3. And we're going to move this to April the 9th. Okay, so instead of, we're going to move it to the Wednesday. Let me just make sure. So yeah, so no, April the 8th. So Wednesday, April the 8th. And the reason why we're going to move this to a Wednesday is because I will then post the Quizam 4 key that you can study and look and learn from the April the 9th. Okay, so we're going to work through the POGL and we're going to work through chapter 22, and then Wednesday, April 8th will be Quizam 4. And then 9th, I'll post the key for Quizam 4. This will not, no replacement on this. Okay, we're not going to have replacement because of the conditions under which we're taking the Quizam again. Now, the other thing, I will post a Quizam wrapper. So Quizam wrapper. This will be Quizam 4 wrapper will be posted next week. So I'll do that on that Thursday of next week under the Canvas. So you'll have that to practice and to make sure you're learning the material. It's very important that you work the weighed problems. I have videos that tell you how to work those, and they're in your Canvas. Okay, and we're looking at chapter 22, the enols and enolates. And I will give you these announcements again. Once again, Wednesday, tomorrow, well, tomorrow, this would be today. Today you do have a quiz, and that you will have your weekly quiz. So you have quiz, I think it's quiz 8, and it's on sapling. And so you have today to do it. You can't go back and change the answers. There's 10 multiple choice questions. And then next week, we'll still keep probably with a Wednesday quiz. You'll have quiz 9, and that'll be on sapling. 10 multiple choice questions. On Thursdays, I will try to give you the key to these quiz questions. And then the following April the 8th, Wednesday, you'll have Quizam 4. Okay, so you're going to have Quizam 4. So you have 2 quizzes over this material, 8 and 9, and then Quizam 4, and that'll be April the 8th. Your intern exam will stay the same date, and so will your final, and those will likely be on sapling. All right, so let's get into our work. We are looking at page 266, model 3. This is reactions, alpha to the carbonyl. So this is your first, you need a reaction sheet. for those of you still doing that. And what's your starting material? It would be a ketone, an aldehyde, or an ester. Okay. And in this case, we're going to really look at ketones and aldehydes. You have to have a carbonyl, okay? And they have to have an alpha carbon that has alpha hydrogens. That's your starting material. Okay, what reagents do you do? Well, in this case, you're going to see that you do LDA, okay? Lithium diisopropyl amide. We talked about that being a sterically hindered Hoffman base. And that way it does not act as a nucleophile. It's not nucleophilic, folks. It will not attack the carbonyl as a nucleophile. Okay? Not going to happen. It's going to act as a base. It's going to take away the alpha hydrogen, and that way you're going to generate quantitatively 100% the enolate. Okay? Remember the monkey face. And then that's going to be your nucleophile. That's what we're learning here. Okay? The product in your reaction sheet will be, you're going to replace the alpha hydrogen with your electrophile. Okay? So sometimes we're going to make carbon-carbon bonds. That's going to be called alkylation. Sometimes you might want to add a bromine there. Okay? And that's halogenation. So let's look at those Model 3. And hopefully you'll be working these, and then you can pause me and try to work them on your own. Because the whole point is for you to learn. Learn to think. Okay, so this is step 1. You do need to know this mechanism. So LDA we'll not work through it all yet here. We'll just this is your enolate ion. And then step 2 is your electrophile. And you see this electrophile here is added to the alpha carbon. All right, so 9A. Label the alpha carbon in the aldehyde shown above. So this is your alpha carbon. Those are your hydrogens. In step 1, LDA is combined with your aldehyde to give the enolate ion. That's step 1. Discuss the purpose of adding a strong, bulky base to the aldehyde. LDA is not nucleophilic. Okay, so it's not going to attack the carbonyl, but it will remove an alpha hydrogen. And that is the purpose. Turn the page to 267. 9C. In step 2, the electrophile is added to the enolate. What is the role of the enolate ion in the second step? So this is your electrophile, and folks, I like to do this, okay? When I'm doing these reactions, I like just to keep it like that because my alpha carbon is my nucleophile. You see, it's got the lone pairs and the negative charge, and so then this can go and attack, right? So the nucleophile always attacks the electrophile, the electron flow arrows. So 9C is nucleophile. Draw the product and the mechanism when your electrophile is CH3 bromine. Bromomethane is used as your electrophile. Once your group agrees with the mechanisms, discuss whether the mechanism supports the roles assigned, nucleophile and electrophile. Okay, this is the mechanism you need to get in your reaction sheet. So we're going to take this aldehyde here. Step 1, you're going to have to show this LDA, so draw that out, goes and label your alpha carbon, drawing your alpha hydrogens, and then you can show these electrons taking, this is acid-base chemistry right here. Okay, so step 1 is acid-base, and it generates, so I'll have one hydrogen there. The other one now is, this is your nucleophile, step 1. And what happened to LDA? Okay, lithium's going to hang out here. And that pKa is 35. This acid pKa is 20. Okay, so this is quantitatively makes the enolate. This is your enolate. That's step 1. Step 2. Now we've added the primary alkyl halide. Okay, now those electrons, nucleophile, attack the primary alkyl halide. The bromine is your leaving group. And then you redraw your aldehyde. And now at the alpha carbon, you substitute the CH3. Okay, and that's your mechanism. 9E. After formation of the enolate ion, what mechanism is occurring on the reaction with the primary alkyl halide? So what is this mechanism here in step 2? SN2, right? Yes, it's an SN2. The reaction is called alkylation. So if you want a name for this, it's alkylation of the alpha carbon. Why? Because you're making a carbon-carbon bond. Okay, now we are on to number 10 on page 267. Predict. These are also reactions you should get into your reaction sheet. So it says predict the products, the following reaction. So here we have cyclopentanone, because it's a ketone. And we're reacting it with 1, first step, LDA, and then 2, benzyl bromide. When you draw these out, I don't want you to write phenyl CH2 bromide, okay? I want you to draw out the structure. So even with LDA, I want to see that structure. Now, the first thing you want to do is you want to find your alpha carbon, draw in your alpha hydrogens, okay? And then you want to do your step 1, which is an acid-base reaction. You're going to remove that hydrogen, and you're going to draw your enolate. Now, for your sake, for on your problems that you're going to turn into me, the additional problems, I do want to see the resonance structure. Okay, so there's your resonance structure. And then for step 2, you can use the monkey face one, okay? And step 2 here, we're just going to do an SN2 reaction. This is a benzyl bromide. So you know the benzyls are fast reacting compounds. This comes here, this leaves. There's your electron flow arrows, and then you have your new bond between your alpha carbon and your benzyl. Okay, so count your carbons, 6, 7 carbons, and this is 5 carbons. 5 carbons, 6, 7 carbons. So yes, that's good. And you alkylated this alkylation of an alpha carbon. All right, what about B? 10B. Got another ketone here. What's this ketone called? 3, 1, 2, 3, 4, 5. Pentanone, not a cyclo. 1, LDA, and then 2, bromine. Draw it out. All right, LDA, we'll go ahead and just draw that structure. Okay, the next thing we want to do, these are symmetrical, so we can just go with 1. There's your alpha carbon, drawing your hydrogens. The base comes and deprotonates. We're going to redraw for step 1. We're going to draw our enolate. Okay, this is our enolate. This is going to be our nucleophile. And the next thing we have to do is draw a resonance structure. There's our resonance structure. And then for step 2, you learned that your electrophile here gets an induced dipole. So the enolate then, we're going to redraw the enolate because I want to show my electron flow arrows. I don't like structures that have more than 2 or 3 electron flow arrows. I will count it wrong, so I have to redraw it to show you that. Here's your electron flow arrows, and we have now added the bromine to the alpha carbon, and there's your product. Your product would be 2 bromo, 3 pentanone. Okay, and this is an alpha halogenation reaction. That would be the name of it if that was your electrophile. Okay, that completes page 267. You have the additional problems 11, 12, and 13, and 14. I do want to see your mechanism on number, I want to see your electron flow arrows for 12, 13, and 14. I will give you a little clue for 13, so I don't get a lot of emails here. 13, these are hard for people, okay? So if I want to make my reactions hard, if I want to give you a harder question, I just give you a cyclization problem, okay? So here you have LDA, okay? So number these, 1, 2, 3, 4, 5, okay? And I'll number these. This is 1, this is 2, this is 3, this is 4, and this is 5, okay? So step 1, do step 1, right? For this molecule. And because this, where's your alpha carbon? Number 2 is your alpha carbon, okay? So step 1 generates this nucleophile. Okay, so there's 1, 2, 3, 4, 5. So that's step 1. Step 2, you get a 5-membered ring. So there's your step 2. Okay, this is called an intramolecular cyclization, and it's very, we're going to see a lot of those. Okay, it's an internal intramolecular SN2 reaction. Okay, so I want you to start looking for that. All right, I promised you that we would do 2 models a day. So even though we're on 20 minutes, we are going to start, I don't think you should do more than probably 2 models a day, okay? And then you should reinforce it. We are starting page 262. We're doing, no, that's not true. 271, all right? So let's erase that. 271. 271, and it is PG23b. Okay, this is the aldol condensation. This should have its own reaction sheet, condensation. So here we have propanol, and the base for aldol condensation is hydroxide, so sodium hydroxide. You just saw the base for the alpha substitution reaction should be LDA. And I introduced this on Monday, that your bases are going to be the alkoxides, LDA, and sodium hydroxide. Okay, we're not going to deal with the acid catalyzed aldol reaction. This whole chapter, I'm going to try to simplify it. Our reagents are going to be the different kinds of bases, and we're just going to stay away from the acid catalyzed. Not that they're not important. I just figure if you learn this, you're good. Okay, so let's just do the base. So it's like Megan Trainor, all about that base. No acid, no trouble, no acid. This is your aldol product. I'm just copying model 1. Okay, and I want you to get these reaction sheets. So this is propanol. So in the aldol, your starting material, it's actually going to be either an aldehyde, you will see, or a ketone. It's kind of like the ketal and the ketal and the acetal. They kind of use it interchangeably. Okay, what you will always see is the aldol condensation. Condensation means it's going to bring molecules together. Okay, and the aldol uses sodium hydroxide. Okay, now you notice we have an equilibrium arrow here. Let's just address this real quick. The last one, LDA, does 100% to the enolate because it's such a strong base. But this one, and it's not really exactly like this. It would actually probably, electron flow arrows would be more like this, because your alpha carbon here with the hydrogens are going to have a pKa of about 20, right? There's an aldehyde. Your OH base is going to deprotonate that aldehyde and give you this enolate, and you're going to get water. Okay, so this is your conjugate base, and this is your conjugate acid. What's the pK of water? 15.7. So we can say 16, 20 to 16. It's going to be 10,000 times towards the product. But why can we use the OH? Because you'll see when the product's made, this is step 1, okay, generating the enolate. And maybe we only generate out of 100 molecules of the aldehyde, maybe we only generate 20 of the enolate, okay? So if we have 20 of the enolate, but then step 2, we react it with the electrophile. And you're going to see the electrophile is itself here, okay? So electrophile in step 2 is going to be another aldehyde, and this is your electrophile, the carbonyl, carbon. So then when this comes here and attacks there to make the aldol product, step 2 is irreversible. Okay, it goes one way 100%. So what's happening is this is constant equilibrium, constantly generating maybe like 20 of these enolate ions, but then they're 100% going to the product. And this is called Le Chatelet principle. And Le Chatelet's principle will keep pulling this enolate away. And so this equilibrium is constantly generating 20 molecules. And finally, I mean, you get down to 20, and then what's the percentage of that? You might get 5, and then you get down to 15, and then you might get 3, and you can see that eventually all the propanol will go away, and that's why you can use sodium hydroxide. All right, let's answer your questions. Ooh, I just lost it. Well, that's okay. Let's see if I can find it back. Yeah, I found it. Okay. So let's answer your questions for 1A. How many carbons are in propanol? So how many carbons are here? 1, 2, 3. 3. How many carbons are in the aldol product? 1, 2, 3, 4, 5, 6. How many molecules of propanol combine to form the aldol product? 2. Using Greek letters, label the carbons of the product. Okay, so here, this is an alpha. The hydroxyl is a beta, and this is a gamma and delta. We really only care about the alpha substitution. So you've made a new, the aldol product would be a beta hydroxy carbonyl. Okay, so it's the beta. The hydroxy is going to be on the beta. You've substituted on the alpha. You made a new carbon-carbon bond on the alpha carbon. So what position does the hydroxyl group reside? The beta. Name the two functional groups in the aldol product. You have an alcohol and you have an aldehyde. So aldol. Al for aldehyde, OL for alcohol. Okay. In the aldol condensation, we got a new one here. In the aldol condensation, notice you draw two of these, and I would recommend you do. You have an electrophile and you have a nucleophile. So this is problem number 2. Consider the electrophile. Circle the atom that is the most positive in the electrophile. So this would be, this carbon here would be the most positive in your electrophile. And it wants to explain why. So let's draw a resonance structure. These electrons go up to oxygen, and you can see that you have a full positive on that carbon. Okay, so there's your electrophile. Okay, now turning to page 272. When the aldehyde reacts with a strong nucleophile, as shown below, we're showing you a new reaction where R can be any alkyl group, and you're reacting it with a nucleophile. You know this. This is what we've been doing since week 1 here. We make our tetrahedral intermediate. We've added the nucleophile on there. Okay. Now what they're trying to show you here is that the carbonyl has now turned into an alcohol, because you would pick up water and protonate that, and then you would get an alcohol. And we've been doing that. Grignards adding to carbonyls give you alcohols, they get protonated. Circle the atom in the aldol product that came from the carbonyl, the electrophile. So if we go back up here to our model, oh, here's our model, or just our reaction. Circle the atom in the aldol product that came from the carbonyl. Okay, so let's draw this product here. So let's draw the Aldol product. So this is your alpha, right? Here's your alpha. And then this becomes your beta. Okay, so your electrophile becomes your beta. So go ahead and we'll make this blue. 1, 2, 3. 1, 2, 3. And then we'll make this one green. 1, 2, 3. 1, 2, 3. Okay, and so the question was, circle the atom in the aldol product from the carbonyl aldol product that came from the carbonyl of the electrophile. So this is the one right there. Consider the nucleophile. So we're looking at the nucleophile now. Which carbon of the nucleophile forms a new bond with the electrophile? It's the alpha carbon, folks. Okay. Draw a box around this carbon. So draw a box. And the nucleophile and the product above. Draw the reaction using the base catalyst that must occur in order to convert the aldehyde into a nucleophile. So all they want you to do is show you that you draw in the hydrogens here. And these electrons take this, and then you want to draw your enolate. It's always the first step. So you just redraw the aldehyde here, and you draw your monkey face here, and so you show your enolate. That's step 1. And then step 2, the enolate will attack the electrophile. So this is step 2. And then what you get is you get, that's an O minus, right? That's this, 1, 2, 3. This is your alpha. And so draw your aldehyde here. And we'll just call this CH3. CH3. And this oxygen negative then has to pick up a hydrogen from the water to regenerate your catalyst. And that's how you get your product. Okay? And that's the mechanism that you need to be able to draw in 10E, but you also need to have this in your reaction sheet. Okay? So step 1, you generate the enolate, and then step 2, it attacks the electrophile. All right, so we have 2 more questions. F, 10F. Once your group agrees on the above questions, discuss why the following aldehydes cannot undergo the Aldol condensation reaction. So these cannot undergo Aldol condensation. Why? Well, the first one has an alpha carbon, but no alpha hydrogens. That carbon is bonded to 4 carbons. This compound has an alpha carbon. This hydrogen is not. That's an aldehyde. Okay, that is not an alpha carbon. Here's your alpha carbon, but no alpha hydrogens. This has no alpha carbon. Can't form no nucleophile, folks. Okay, can't form it. Okay, we're on page 273 to wrap up today's lesson. Devise a mechanism for the aldol condensation using curved arrows. Okay, so let's draw this one all out. First thing you want to do is react. You got it. Step 1. Form your enolate. So identify your alpha carbons, draw in your alpha hydrogens, draw your enolate. You just redraw that aldehyde, put in your monkey face right here. Now, I want you to draw your resonance structure. Okay. There you go. Now, step 2, this in the Aldol reaction, it reacts with itself. So you got to draw another molecule, and this one's going to be your electrophile. So this is your delta positive, the carbon. So these electrons will come here, attack that carbonyl, and now just redraw your aldehyde. Okay, so we'll make this one blue. 1, 2, 3. This is your alpha. 1, there's your alpha, CH3, CH3. And then this formed a new bond with this carbon. Okay, so 1, 2, 3. And this negative then will pick up a water, hydrogen, to regenerate your base, to give you your alcohol. Count your carbons. You should have 6. 1, 2, 3, 4, 5, 6. And that is your aldol. Alcohol, aldehyde, aldol product. So at the end of this lesson, you need to do your POGL additional exercise from PG23a, and the next lecture video will be completing 23b.